So this recording is to try and give you a little bit of a refresher on periodic trends. Last year we covered four of them. We talked about ionization energy, electronegativity, atomic radius, and ionic radius. And for the most part, it's all the same. We're going to add a little bit of something called electron affinity, but for the most part, this is going to be very similar with just a little bit more detail. Okay. So the first trend I'm going to talk about is ionization energy. And really to understand the trends, you really have to understand the definition of each one of these. Ionization energy is how much energy it takes to pull an electron off a gaseous atom. So if I have a gas element here and I rip an electron off of it, it's how much energy it takes to do that. Now, I know we've talked about how some elements want to give away electrons and others don't. The bottom line is electrons are always attracted to a nucleus, and therefore it is always endothermic if you're going to remove an electron. Now, some things give up electrons easier than others. It is still an endothermic process. It just may not be very much energy to remove it, but it is still energy all the same. So these are always endothermic processes. It is always the highest energy electron, and when I say the highest energy, I mean the highest energy level around the nucleus, around the atom, that is the one that is held the least tight to the atom. And therefore, that's the one that's always going to be easiest to remove. So every time you take an additional electron off the atom, it is going to be more and more energy. The closer it is to the nucleus, the more bound it is or attracted to that nucleus. Therefore, the more electrons you take off, the more energy it takes. So the one on the outside is always the easiest one to take. So the first electron removed from any kind of neutral atom always forms a positive cation. And every time we increase the positive charge in the nucleus as compared to relative amounts of electrons, again, that helps to hold the electrons more firmly in place. Anytime we get past the valence electrons are far easier to take than the core electrons. So the outer side or the outer edge electrons, the valence electrons, are always easier. Once we get past those are called core electrons, the ones that are on the inside of that outside energy level. Those are always held much tighter, and the energies to remove these can be extreme. So first ionization energy, the trend is going from left to right, it increases, okay? And the ionization decreases going down a group. Okay, so let me just pull up my periodic table here and see if this helps to make a little bit of sense here. Oops, that's a little bit too small. All right, so as I'm moving across from left to right, if you think about it, each one of my elements from lithium to beryllium to boron to carbon and so forth, as I go left to right, I am increasing the positive charge of the nucleus. Each time I am adding a proton, making the nucleus stronger. And as I do that, obviously the electrons are going to be held much tighter. Okay, so increasing ionization energy increases from left to right. Now going down on the periodic table, it's going to decrease. And if you think about it, so going from lithium to sodium to potassium, we're adding energy levels. The distance between the outside electrons and the nucleus is getting farther apart. So as this distance increases, these electrons are easier and easier to remove. Okay, hope that makes some sense. Now, the trend is pretty solid in terms of there's a little bit of variation, but there is some. So I wanted to show you this graph from the book because we start to see a little bit of bumps in the pattern, because this is going from left to right, hydrogen, helium. And again, if you look at that periodic table, lithium, beryllium, boron, carbon, that's what we're going to see in this next trend here. Lithium, beryllium, boron. And if you look, there's a little hiccup here between beryllium and boron. Boron has slightly less energy to remove that electron, okay? And then we have another hiccup between nitrogen and oxygen. So let's look at the periodic table and see if we can't see what's going on. I have a hiccup between beryllium and boron. So in between here, boron's electron is just a little bit easier to remove than beryllium's, which is not in the trend. It's supposed to increase. But what's happening between beryllium and boron is I'm starting a whole new sublevel. I went from filling the S sublevel to the P sublevel, which means boron's electron here is kind of sitting all by itself out there, and so it's just slightly easier to remove. The next hiccup we saw was between nitrogen and oxygen. And if you think about what is happening in terms of electron filling order between nitrogen and oxygen, this is the first electron that's actually doubling up. And if you remember when we were talking about axes designation for electron configuration, boron would go in the X, carbon would go in the Y, nitrogen would go in the Z. Oxygen, however, is the first one that's going to double up into the X axis. Because electrons don't like roommates, they don't like to share, this electron, that oxygen added, is slightly easier to remove because it's the first one that ends up having a roommate. Okay? And if we see this pattern, this hiccup happens in the same place every time, from my sodium to magnesium, and then there's a little hiccup here, this little bump that doesn't follow the trend. That's when my S becomes a P sublevel. Between phosphorus and sulfur, this is where my axes start to double up, X, Y, Z for phosphorus, and then my sulfur has to double up. So again, we keep seeing these kind of little variations throughout the ionization energy. But in general, the pattern holds pretty true, okay, from left to right and top to bottom. So electron affinity is one that we did not really cover. We really talked about electronegativity, which is the same idea. It really is, except that rather than electronegativity, which was an arbitrary number from 0 to 4, like how much elements can attract electrons, electron affinity is actually an energy measurement. So it's how much energy is released if an element in its gas state receives an electron. And again, since electrons are attracted to a nucleus, giving an electron to any atom like this is going to be an exothermic reaction. So pulling them off is endothermic, giving them back is exothermic. And because they're exothermic, you know this now because we just went through thermochemistry, negative just means flow of energy. So when we have higher negative numbers, that means this is a more exothermic process. So let me say that again. The negative sign means energy is released. So the more negative the number, the more energy that's released. So electron affinity follows the same pattern that you would expect it to with electronegativity. It's just that we're talking about negative numbers. And since first year chemistry, we don't really talk about thermochemical processes. Therefore, we don't really talk about electron affinity. Rather, we just call it electronegativity. So it's a little bit easier. So again, the addition of an electron is exothermic, and therefore the values will always carry a negative sign. The more negative the energy, the greater energy that's being released. So electron affinities generally become more negative from left to right. So again, let's think about this from last year when we were talking electronegativity increased from left to right. Well, so does electron affinity. It's becoming more negative because the energy is increasing. The amount of energy being released is increasing from left to right. Going down a group, and again, thinking of electronegativity last year, electronegativity decreases going down a group. So as it goes down, it becomes more positive or less negative. Less energy is being released as we go down. Okay? As with ionization energy, of course, we have some exceptions here and there that occur to different repulsions in the electron configuration, but generally speaking, we have this pattern that's followed. So again, if you look at this graph, it's a little bit harder to read because we're talking about negative numbers here. But hydrogen, lithium, if you notice there's no helium here because if you think about it, helium is a noble gas and do not accept electrons. So you don't see any kind of noble gases listed here, okay? Again, a couple of hiccups every now and again because of the electron configuration, but the general rule still applies. These are just some common electron affinities of the halogens, because we all know that halogens love their electrons, so giving halogens electrons ends up giving us quite a bit of energy, and if you look, these are listed in kilojoules per mole, so some pretty big numbers there. Something that we probably didn't expect, though, is chlorine's electron affinity is actually a smidge higher than fluorine's, which is not necessarily what we expected there. All right, so atomic radius, this is a complete repeat from last year. Atomic radius is, of course, this idea of radii. It's really measuring size, but we're talking about the radius of the neutral atom. Covalent atomic radii are assumed to be half the distance between the atoms' covalent bonds. The metallic atoms, they bond a little bit different, so they're obtained with half the distance between the metal atoms in a crystal. This is kind of detail here. It's nothing I'm going to quiz you on, but just so you know, they are measured just slightly different depending on the bonds that they have. So atomic radius decreases going from left to right, and I know this is a big misconception, and it's hard to kind of grasp here. I'll pull the periodic table up here in a minute, but it's because of the nuclear charge increasing, okay, and decreasing shielding. Atomic radius increases going down a group. This one most people get right because we're adding energy layers. Of course, that adds more repulsions, and the atoms get bigger. But let me find my other periodic table here. That's not it. Sorry, just a second here. Here we go. Okay, so atomic radius going left to right gets smaller. Let's think about this. From lithium to beryllium to boron, we're adding protons to the nucleus, therefore making the nucleus stronger. We have a more effective nuclear charge, okay? When I'm going from lithium to beryllium to boron, I'm not adding another layer of electrons. I'm adding electrons to the single outside layer, but I'm adding full layers. So there's no additional shielding as we go across the period here, but I am increasing nuclear charge, therefore we get smaller going across. Going down a group, however, from hydrogen to lithium to sodium, I'm including full layers of electrons. And each layer, this kind of layer of fat, if you will, that goes around the atom, each layer is made of negative electrons, therefore repelling the layer underneath it. So these things start to get really, really large as they kind of pile on these layers. So from left to right decreases, from top to bottom increases. So we see something like this general pattern. This doesn't, this is the periodic table or graph of the periodic table. It does not include the transition metals, but as you see, they get significantly bigger as they go down and get smaller as we go across, okay? And that's pretty much going to cover it for this section. There's very little left in the unit, and please, as usual, let me know if you have any questions, okay? Thanks.